exercises. Aims of experiments. This is actually taken from experimental psychology research. The first two are probably the most widely accepted in the industry around the aim of an experiment. An experiment needs to be valid. So does the experiment show what you want it to show? There's no point setting up an experiment, looking for an impact on a variable, not seeing it, but then finding an impact somewhere else. That doesn't count. The experiment wasn't set up to measure that unless it was a secondary KPI. It's probably best to be able to rerun the experiment if you see an impact somewhere else. Rerun the experiment, validate it properly. Experiments need to be reliable. This one probably doesn't apply as much to you guys, but one of the things I always tell my team. So I head up the analytics team at Moore in London. We're scaling our experiments program, so we're really early on. At the start of the year, we've done none. We're currently up to 32. The goal is to get to 50 by the end of the year, 100 by next year, 150 blah, blah, blah. So no one's probably going to redo the results you've already done, but documenting them in a way that they can be redone is valid when you come back to look at what's been done and documenting it. And finally, experiments must be important. I put an asterisk by this again. Reason is, usually experiments, when they say experiments must be important, is because in the world outside of digital, experiments are really expensive. You need to collect lots of people, you need to put them into groups, and it becomes a very expensive process. In our world, we're a bit spoiled for choice. We get a shit ton of traffic, we get thousands and thousands of visitors per day, per week, per month, and it's easy to run even the smallest of experiments in those tests. So importance, you don't have to worry about too much if you're spoiled for traffic. But when you start scaling experiments, certainly having a prioritization process is worthwhile. This isn't going to be around prioritization, but there are many prioritization models out there like RICE, DICE, and whatever it might be. Very quickly, experiment cycle. You can modify this for each company, but a good experimenter will roughly have this cycle in their experiment program. So you have a hypothesis, you do some pre-experiment analysis, you design your experiment, you build it, you set it live, you monitor it, and then you conclude it and you do some type of post-experiment analysis. I think most companies will follow something like this. Is there any steps that I've kind of badly missed?
Making sure you act on the post-experiment analysis.
Yes. You have the action to act on it, then, of course. At Moore, we kind of actually facilitate the other team, so we give them recommendations. If it's a positive result, we should act on it, but otherwise, why run the experiment? Things to consider. So when you're designing your experiment, there's four things that you really should consider. Your data. If you can't track your experiment, there's literally no point in running it. So before you start your experiment, check the metrics, check your goals, check your events, check how much traffic you're getting to that site. Can you count and measure what you've just done? Confounding variables. So confounding variable means your experiment will be exposed to two types of variables, systematic and unsystematic. The systematic ones are the ones you have full control over. The unsystematic ones are the ones you have no control over. They're going to be the things that people in your organization do, and they don't tell you about it. And that will happen. So you'll get people who might suddenly introduce an offer code onto your website, may not even get some randomly distributed between 2 or 3 groups, whatever you're doing. You might see some changes on the site. We ran an experiment, and our CMS team who updated our code, they only updated one version of it, so whilst the experiment was running, our homepage had 2 different designs on it, and it introduced an unconscious bias into our experiment. We thought it failed, actually there was an external influence. So control for confounding variables where possible. Randomization, most of you here will probably use Optimize, the Qubit, A/Tasty, Google experiments, right? They should theoretically randomize the traffic for you, and that randomization will help control for confounding variables. In most cases, like I said, it's only really the stuff early on that you probably won't have control over. And finally, conflicting tests. Having a view of what's running where, when, will help you prioritize your experiments better. It will allow you to see what's going to conflict. For example, if you're running a pricing test and you're running a shipping test, you increase the price on one side and you reduce the price on the other side, you might negate any effects you've had on the other side. So really quickly, that was 2.0 around what experiments are. 2.1, hypothesis. Again, I'll kind of jump into this really quickly, but a couple of definitions from Google. I'm going to focus on the second one. An ideal explanation for something that is based on known facts but has not yet been proved. We don't have this luxury in our industry. There isn't a journal or a database where we can see what other types of experiments have been done. Our biggest resource is to use the information that we have access to. So look back at your historical trends, look back at your data, look back and see what you've done, how you've moved variables, and try to use that as your, I won't say known fact, but realistically, in the digital world, it's a prediction on the outcome based on an introduction and modification of some supposedly related variable, usually with little reasoning. So we don't really reason around the changes we're going to make. We just assume that by changing the price up or down, we're going to have an impact on whether people buy or not. It's a fair assumption to make, but you use the experiment to prove that relationship. Hypothesis is going to have three key things: a dependent variable, so what you'll be measuring; the independent variable, what you'll be testing; and the prediction of the effect on the independent variable on the dependent variable. They should also be clear, understandable, testable, and measurable. So if you write a hypothesis that's a bit wishy-washy, a hypothesis should clearly set out what you aim to prove or disprove. There are many frameworks out there. This is the one we use at my company. So by modifying, introducing the independent variable, we expect a change in the predicted behavior, leading to a directional impact on our dependent variable. So it's really basic. So by changing the price of something, we expect customers to not buy this and buy that, leading to a change in our overall AOV or whatever it might be. So there are a few of these that exist. I will send this around, by the way, it will be on the MeasureCamp website, so if you do miss anything, don't worry about it. The null hypothesis, this is in English. This is the statistical notation of how you test what you're hypothesizing. So your H0 is your null hypothesis. This is the opposite of what you're trying to prove. This is saying, if you're testing an AOV, this is saying that the AOV in group 1 will be exactly the same as your AOV in group 2. And then your alternative hypothesis, what you're trying to prove, is that they won't be the same. So it could go up and down. So we use non-directional in this case because AOV could go up or down depending on what you're doing, and use two-tail tests, one-tail test. But essentially that's what it is. A note on null hypothesis, why am I talking about it? Why don't we just focus on the hypothesis you're trying to prove? You can't prove your hypothesis, you can only disprove your null hypothesis. So if you've never heard that before, it's just bear with me. So we can only disprove the null hypothesis. If we disprove it, we reject the null hypothesis, then it doesn't mean that our experimental hypothesis is correct, it simply means we have evidence to support the experimental hypothesis. But if the opposite happens and our experiment loses, in that case, it didn't lose, we simply failed to reject the null hypothesis. Like I said, it's really fast, it's really dirty. This is going to be just...
It's like a jury trial, innocent until proven guilty.
Yes, that is actually a great way to look at null hypotheses. Variables. I'm going to skip, I'm going to discuss dependent and independent variables because I promised I would. The dependent variable is how much you will like this training session on a scale of 1 to 10. The independent variable is how many hours I put into preparing this. Now, there may be no relationship. You guys might absolutely fucking hate this session, despite the fact that I put something like 20 hours into putting it together. Okay? So,
You've been in emotional psychology there to
yes, this is me absolutely introducing like some kind of unconscious bias. I'm going to skip over experimental research and non-experimental research. I will move on to categorical variables and continuous variables. There are two types. Categorical, these are the ones that don't have magnitude. These ones are the ones you can't really measure. Nominal, so these are your hair color, your city you live in. There's no value associated with each one. Dichotomous is a special type of a nominal one. It just means 1 or 2. So you're male or female. That is a nominal dichotomous variable. And ordinal. These ones have order but not magnitude. So you're running a race. I come first, Alex comes second, and you come third. We can't apply differences in there. It's only when we look at the times that the race was running that you start moving into continuous variables. Interval continuous variables. I don't know why I'm talking this all here. These are the variables where you know the order and the difference between the values. You can add and subtract, but you can't divide. So an example of this is temperature, because temperature doesn't have an absolute 0. Don't ask why. We're going to move on to ratios. Ratios are the ones that you guys will deal with on a day-to-day basis. These are the ones that have an absolute 0. You can't get negative height, you can't get negative money. Well, you can if you look at my bank account, but you can't get, what have I got here as examples? Negative weight, as much as we would like that. You can't get negative AOV, and the order happened or it didn't, right? You didn't suddenly, unless you do a refund. Those continuous ratios can be broken up into two types, proportions and means. Again, just trust me on this. Proportions are the rates. These are the ones where you have a population and a small sample of that population did something. It's not whether they did it or they didn't. Most of these are dichotomous. So dichotomous exists in a categorical sense, whether you're male or female, but also exists in a continuous sense where something happened or it didn't. Mean also includes something happened, but also to what degree it happened. So an order was placed, but of what size? Was it £10, £20, £25, £25.50, etc., etc. Lifetime value, blah, 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 etc. Revenue per visitor is a special metric, I put it in bold. It's a composite metric. It's AOV multiplied by conversion rate. So you have a bit of both, but it would fall into the latter category. Like I said, sorry, this is really fast. I'm really, really sorry. Anyone feels free to stop me and ask a question. When you're thinking about designing your experiments, I use the earth. This is an analogy I created. It's an earthquake analogy. So imagine you're running your test at some part of your website. This is your test epicenter, and this is where you're measuring the impact. The further away you get from your test center, chances are the intensity will start to dampen, even if the magnitude was really high. So imagine this. There's this earthquake. I'm really sorry if there's any earthquakes going on in the world right now. Imagine we have an earthquake in London. Hope we don't. That's of magnitude 10. It's fucking huge, but they're probably not going to feel it in India. Right? So that's how you look at it. So pick variables that you can feel, and definitely measure for secondary variables if you need to, but keep in mind that conversion, AOV, they shouldn't be the variables that you always look at. Consider your micro KPIs and macro KPIs. So what are our independent variables? This was actually a discussion that we had in the group. I'm going to tell you. Your independent variables are things like your prices, the images, the text you make, the change you make on your text, the headline on your email, the form that you compress or you don't compress, the color of the button, despite what people tell you, apparently is an independent variable that we all know it doesn't work. And so if anyone has proven that, I'd like to see the stats. Pre-experimental design, analysis. So we've designed the experiment, we kind of know what metrics we want to measure, we know what goals, the data's there, it all exists, there's no conflicting variables. Now you want to do some analysis around it. So, to me, pre-experimental analysis is the most important step, but it's a step that a lot of people do miss. Not everyone, but a lot of people do miss it. Most people skip it or place little importance to it, and the reason it's important, in my opinion, is it helps you understand the metrics you're about to study or experiment on. A good pre-experiment analysis will determine whether or not even an experiment should run, where it should run, and for how long. It will also help you describe your data, show how steady the numbers are, and to what degree of variance you should expect. Why is this important? So understanding how fluctuated your data is will help you manage people's expectations. So if you have to tell your marketing team that
sorry, just one question. Could you call this kind of stage experiment design in a way, since you'll be designing which type of experiment and which type of approach or statistical approach you'll actually be taking that fits the...
Yeah, so we cover that off in the future slides. So we do cover like Z-tests and parametric tests and non-parametric tests. But this is, again, like I said, important. When you are telling your stakeholders how long you need to run the test, it helps manage their expectations. If your data is, I'm going to skip this, you trend your data. I hope everyone trends their data at some point just to see what it looks like. This is your data represented in numbers. So the standard deviation will determine how spread out your data is. Now, I use the example I would use, if Bill Gates, so right now, our standard deviation is going to be quite low. Our salaries are going to be quite similar with various fluctuations. If Bill Gates and Elon Musk walked in, we would all become, on average, millionaires, and our standard deviation would be straight, like, I mean, we won't be millionaires, but the data would make it look like we're absolute millionaires, but we're not. At this stage, it's also important to know what type of traffic volumes you have, because you'll need them later for your sample size calculations. Again, another note, the graph there is normally distributed. I will talk about why all of this stuff is important, but running some type of distribution analysis to understand how your data looks is important to determine which test you use. Sometimes I'm going to cover that. Yes?
So, for example, when you're measuring conversion rates, you can't get conversion rates less than 0. So you get that kind of log normal distribution where you get heavy outliers like the Bill Gates dragging the average up.
Yeah.
Obviously, when you compare everything on the same model, the averages are all calculated in the same way.
Yeah.
But do you look at any kind of quantiles or medians or any
So,
other basis?
I've got a section on outliers. So we try and use outliers, and because we take the standard deviation into consideration, and there is an example where we kind of use the 90th percentile to calculate sample sizes. I think in a traditional sense, you'd probably try to use all the data you have, but when you are limited on traffic, we're not saving life, we're not doing making drugs that's going to make people's lives better. I think it's okay, in my opinion, to fudge the numbers slightly, just like lower that confidence. I mean, fun fact: 95% confidence isn't a calculated metric. Some guy woke up one morning and said 95% confidence is what we're going to use. So it's like, this is why I love statistics. It's all probability. It's all.
Swear jar, it depends.
Oh, sorry. It does not depend. Again, I'm just really conscious of time. Pre-experimental analysis. AOV and revenue per visitors. These will normally follow. These will usually follow a non-normal distribution, but it's a good idea just to trend some of this analysis, some of this data out. Look at your mean, look at your standard deviation. What type is it skewed, and is it revenue per visitor? But when you talk about what a skewed mean, a normal distribution will follow this bell shape. Everyone's familiar with it. The mean, median, most sit on exactly the same line. The positive skewed, if you're a company that has low value products, chances are you're probably a bit more positively skewed. We sell slightly premium products, so our AOV sits more on this side because in comparison to we have more high value products in comparison to our low value products. Standard deviation, normal distribution. I covered off that the dispersion of data. This is my Bill Gates example. Most of us currently are in here. So the average standard deviation for the average mean of these graphs is both 100, but you can see that the standard deviation differs, and that's where you get some wider dispersions. And all of this comes into consideration when you do sample size calculations. 95% of your data for a normally distributed set will sit within these first two standard deviations. Standard deviation is, this graph is your mean, one standard deviation, so £50 AOV plus £6. So the mean is here plus £6, so £56 either side, £6 either side. Second one is slightly becomes a little bigger. Sorry, it's so British, I apologise not too much. Trick question, it was a trick question yesterday. Which one of these is the most, has the highest standard deviation? Anyone throw? We'll just do a show of hands. 1? 2? They're percentages. I'm talking about in absolute values. So this one is a percentage because it's a conversion rate. These two are AOVs and revenue per visitor. So these are currencies. So hands up if you think this one is the most dispersed in terms of its data set. 2? 3? Cool. All of you threes are wrong. It's actually this one because it's relative to the mean. Right? So the standard deviation, £5 mean with a £3 standard deviation is going to be something in the region of 60-70%-ish. This actually is a very low standard deviation in terms of mean, in terms of its actual mean. So actually, our AOV is far steadier than our revenue per visitor, even in comparison to our conversion rate. So keep that in mind when you are looking at this data. It's relative to the mean. It's called confidence of variation, by the way. Look for outliers. This is actual data for one of the tests we ran. We did some descriptive analysis on our data. We found that on the entire data set, we had a £54 AOV and £122 standard deviation. That should ring alarm bells. That should absolutely ring alarm bells to try and do some type of Z-score or observational analysis on outliers. When we removed it, this was that 90th percentile thing. We actually first just removed the outlier, and then we also looked at the 90th percentile. When we removed the outlier, we got a £43 AOV and a £46 standard deviation. Why are we talking about these? Because they're important. You need them to calculate sample size in one statistical test. Sample size calculation requires 5 things. I've covered 2 of them. The standard deviation, the alternative hypothesis, and the direction you're looking for. Is it going to be 1-cell or 2-cell test? The desired significance level. The probability that we'll reject null hypothesis if it's true. Desired statistical power, the probability of detecting an effect if it exists. I have a beautiful example to highlight what this means in just a second, and the size of the effect we're looking for. This one's kind of subjective. Usually you use previous research to do this, but as I mentioned, you haven't. So if you're looking for a small difference, which sometimes can add up to thousands and thousands of pounds, but if it's going to take 100 days to validate, it's probably not worth running it. So it's going to be quite subjective, and I'll come back to that. Type 1, type 2 error, this is what it looks like on a graph, but fuck that shit. Let's go into the really fun visual. This is a type 1, type 2 error. Yeah? Clearly, this is random and it's not normal. She's clearly pregnant and we're missing it. So this is quite important in the pharmaceutical industry. It's okay, really morbid example. It's okay telling someone they have cancer when they don't. It's not okay telling someone they don't have cancer when they do. Right? So in this case, you don't, it's maybe not for pregnancy, which you should know, but you want to ensure that you don't tell someone that they don't have cancer if they do. So in the pharmaceutical industries, it's worse to make a type 2 error than it is to make a type 1 error. Most of the things I've seen in the kind of 4 or 5 years I've been doing this, I rarely ever see people accounting for type 2 errors. So I'm here to change that. An example of effect size. This is an actual, we did some pre-experimental analysis. Our team wanted to know how long they should run an experiment for. So we looked at the target means, and we tried to work out the effect we wanted to see on our average mean. And we did some calculations, and we said, well, if you're going to look for a 0.5% interest, first of all, it's not even worth your time because it doesn't add up to that much money. You could look for a 1% impact. We do get a lot of traffic. We're spoiled, as I said very early on. We get a shit ton of traffic to our websites to be able to validate slightly smaller things. When you're doing kind of like psychological research or drug designs, you want to look at huge impact. It's not really worth it for those small impacts. But as I said, we're very spoiled for choice. We can do it. The company has never moved their metrics 2%. So I told them, you can look for it, but chances are it's not going to happen. Post-experiment analysis, statistical tests. Okay, this is the part where it's quite complex. Most of the tests you guys will use assume parametric conditions. So the data is normally distributed. You've got a minimum sample size of at least 30 people, which shouldn't be worried too much. And the data come from 2 independent groups. So it's not one person measured, something that's done to me and then I'm measured again. It comes from 2 different independent groups. If you're unsure of your distribution, there are tests that will account for them, but they're very strict. Now, these don't assume non-normality, they just lower those conditions slightly. So if you're unsure, if you're on the fence about it, if you don't know how to do the test, you can do these slightly harder ones. But in general, for proportion tests, you can use the Z test. And the reason is because of the beautiful thing that is that rule. I always forget the name of it. You know where the proportions, the distribution of the proportion. I've forgotten the name of it. Central limit theorem. The most beautiful thing in the world, central limit theorem, right? And then for means, if your data is parametric, you can use Z test. If it's not, you can use the Mann-Whitney test or Crossfield-Wallace if you're doing ANOVAs and multiple variances. So again, so how do we calculate sample size? I have a dream. I see a world where people don't use crappy online calculators. Okay, that is my dream. So I'm going to introduce you all to G-Power. G-Power, this is, like I said, this is a rapid fire course. G-Power is fast becoming my favorite tool. It allows you to do everything you need to do plus more. It allows you to calculate the sample size you need just by inputting some of the variables early on. So what's your current conversion rate versus what are you looking to measure against? What is your alpha value? So is it 0.05%? And what is your power value? So you're looking for, most tests will be 0.05 on your alpha and 0.8 on your power. So again, take it for face value. If you want to be stricter, you can play with those numbers a little bit, but for most people this is okay. For our marketing team, we had to fudge these numbers a little bit because they only had like 11 clicks a day on their PC ads. And they needed some results quickly. A pre-sample size calculation is called a priori. You can also do a post hoc analysis, which looks at, if you haven't done it, and if you haven't done a pre-sample calculation, you've got a test running, you want to see how it's doing, input the numbers into this, and it will tell you how it's doing. I haven't got it in here. But it will tell you what the statistical significance is along with the power. So you could have high statistical significance, but it could be a very underpowered test. So if you're not seeing much difference or whatever, you might be missing an effect or something. Again, I'm talking very fast here, so I want you to compose it. So, and then this is for the mean. So you just literally put your mean of group 1, mean of group 2, standard deviations for both groups. If you don't know the standard deviation for your control group, your variation group, because you haven't run the test yet, just assume similar. I think these tests are quite, they're powerful enough to play with some fluctuations. And even if you don't know if your test is parametric or not, for the sample sizes that we're working with, you can use those Z-tests and stuff. They loosen the conditions slightly, but they're generally powerful enough to detect things. So, key points: ensure your hypothesis is testable, define direction of hypothesis, clearly identify dependent and independent variables, ensure your tools are able to detect and measure, control for confounding variables, ensure the tests are valid, reliable, and important, describe your data, use the described data to estimate sample size, what's the effect you're looking to achieve, and which test should you use. Now, this isn't scalable. I can do this at Moon because we're only running like 12 tests a month. When we start getting to my 2-3 year plan, we need to automate a lot of this. So this is, if you're really early on, you want to understand some of the mechanics that go into the experiment design, this is what this is. So I would recommend doing it. Does anyone have any questions? Yes?
Not a statistician, I need to solve this. So. What about if you want to use just the base theorem instead of like all of this? Because for a non-statistician, or
Yes. So this is, okay, that's a good point. This is all frequentist ideology. Actually, ideology is the wrong term. It implies some type of weird religion. A lot of the tools you guys will have like something called a Bayesian calculation. So Optimizely has something called Stats Engine, which allows you to get results faster. You're either one or the other, in my opinion. We've got a whole bunch of experts here. I'm more of a former. Reason being is because Optimizely has let me down multiple times, and I have stakeholders screaming at me saying, "Look, big red word that says loser after day 2, and after day 7 is normalized into something really like insignificant." So I love maths and I like this Bayesian method. Some of the more stat stuff is a bit above my head. I will get there. I become really obsessive when I get to that, but for now I'm very much so. Craig, please.
The whole point there is that not everybody needs to know exactly how everything inside the nuclear reactor works. It's able to make a decision when you ask them a question about what should we do with staffing or something else. Not expecting CEOs to understand the statistics. I think you have a different plugin for different types of tests. That's your stack.
Yes.
We've got some pre-prepared stacks here we use for different kinds of experiments. They don't need to know how the stacks work. What they want to know is, what do I do? Do I leave it on the site? Do I put the old one back? Do we keep running the test?
Yeah.
It's decision making that this supports, right?
Yes.
So if you were saying earlier about the risk, when you're talking about minimizing the sort of quantifying risk, if you're not so good on the stats but you want to trust the tool, you tend to need to do tests that are clear, so there's going to be a big difference, and you tend to either err on the cautious side, so don't trust the tool and when it goes winner, give it a bit more time to run the sample, or go, we normally coin flip, 60% is good enough, we want to be fast, but understand you're taking more risk when you do so. So test the sort of stuff to the level you want got the ability to. When you get into the nitty gritty and you're trying to separate the 7 decimal places, yes, you need to pay attention to this shit, but you shouldn't jump into that level first.
No,
So
yeah.
it's ridiculous that everyone's tests are 95%. And if you walk into a supermarket and say, oh guys, everything you change in this supermarket and all across Tesco in the UK, do you test them to 95%
No,
confidence?
exactly.
Also, different risks and different experiments need different criteria and judgment for whether they won or not.
And also I think
found that choose between we're going to run one of them.
Yeah.
Either don't run the test at all, that's no damage thing. It's not going to make a big enough difference to pick the one you like.
Yep.
Or run to a much faster, much lower significance and power because you need to decide in 2 months because Christmas is coming. And that's it.
So would you say it depends?
It doesn't depend. Your risk goes up with the decisions you make. I would say. Your risk goes up and down. And I like my team to control for risk because we're at a stage where we're trying to get change or shift in our company's behaviour. They've been very gut decision based. We're trying to introduce decision making. Yes, Reese.
Sort of following on to the like off-the-shelf tools questions, I guess, but like you talked about a lot of things that are very specific to analysis. You do like the outliers, looking at the distributions, whereas all the off-the-shelf tools you can literally just throw any test metric into them and expect to get a result.
But they don't all ask you to play around with the alphas and the betas.
Well, that's what I'm saying. I guess because they don't ask you to do that. Like, how well do you feel they handle that stuff?
Oh, that's I don't know.
Throw everything at them.
Well, this is why I don't like it. I don't like trusting a black box. So
One point, they all, most of the tools all have an MDE calculator. What's the expected effect?
Yes.
And that's the one variable in those things you can change. So when you're saying how long should my sample be, they've all got minimum detectable effect, and they phrase it as how much uplift would you like to see?
Yes.
And people go 20%. You want to do 20%, but that's actually one of the factors in that sum.
Yeah.
What you want to do is what Bhav pointed out, like, have we ever seen a 20% uplift from anything we've ever done? If the highest you've ever seen is a 2% shift, that would be the minimum detectable effect, and that will then tell you if the sample size you've got is going to be enough to do it in a reasonable period. So the MDE bit is not an option.
Yep.
That's the only part of control that those tools give you to do that.
And if you aren't seeing those 20% uplifts on anything, then you have a really bad website.
Guys, I think we're coming up to time, right? So I want to finish with something. I can take a private question afterwards, unless it's where's my bedroom. In which case it's in North I call this a love affair with experiments. Sometimes we're normal, symmetrical around mu, like yin and yang, positive, negative, sometimes we skew. Like a null hypothesis, you love to reject me because of something you believe, that we're just an example of two different samples from two different populations, but if we put aside our differences, we can create a better hypothesis. You say I'm needy, I'd say I'm dependent. Your p-value's been abused, now you're isolated and independent. Trust me, you're not alone. This relationship, it can be mended. It isn't categorical, it's not black and white. It's not dichotomous, this is 50 shades of grey, passionate and continuous. Even two different standard deviations can have the same mean. Let's not reject each other. You and me, we're not that different. We're strong and powerful, and the difference as well is statistically insignificant. This will be available online. I will do the 3-hour session again at the next MeasureCamp.
Is the poem going to be included in the slides?
It's not finished. It's not finished.